Hello everyone, welcome to this lecture. Last lecture we discussed the cross-sections of nuclear reactions. We discussed the cross-sections for neutron-induced reactions and the charged particle-induced reactions. In the case of neutron-induced reactions, cross-section decreases with increasing energy of the neutron. Then in the intermediate region there are resonances. Whereas in the case of charged particle-induced reactions, cross-section increases beyond a threshold value of ECM equal to VC, and after that it goes rising. We also saw how to determine the cross-sections experimentally by measurement of excitation functions or even by measurement of particle spectra and angular distribution. Today we will discuss the mechanism of different types of reactions, and mostly I will be focusing on the dominant mechanism, that is the compound nucleus reaction. So just let us see in a nutshell what are the different types of reactions that occur when a projectile bombards a target. So I have given a schematic here. This is actually in the time zone as a function of time, how it is happening. So the projectile is bombarding a target nucleus, and many a times, what will happen, in fact it is always there, a component of elastic scattering. Elastic scattering is nothing but a sort of a billiard ball collision between the two bodies, a projectile and a target. And then this, in the elastic scattering, I will be discussing very shortly what are the things that are conserved, which are not conserved, and so on. But this is actually not included in the nuclear reaction component. And this elastic scattering is always there whenever a reaction is there. So it can happen immediately. That is what is I have written in the initial stage, that projectile just collides with the target and undergoes elastic scattering. In fact, that Coulomb scattering, other force scattering, is also coming in the category of elastic scattering. Then we come to the intermediate zone, where the projectile is now coming in close vicinity of the target nucleus. And before that, in fact, before it is completely fusing with the target, there is a type of reactions called direct reactions. That means the projectile comes close to target nucleus, and there is a transfer of few nucleons from projectile to target, or vice versa. So that happens at a much smaller time scale than the compound nuclear formation, which we will discuss in length later on. And many a times, they can form a compound nucleus. The compound nucleus part we will discuss in detail in this lecture. And the compound nucleus can again, give rise to that projectile back. So it is this is what is called the compound elastic scattering. The projectile, it is like, projectile goes into the well of the nucleus and comes back with the same energy as it entered. So this is called the compound elastic scattering. There is a very small difference in the phenomena of elastic scattering and compound elastic scattering. And then the last stage is the compound nucleus formation that takes place after a lot of time. Now the time scales, in nuclear reactions will be for elastic scattering and direct reaction 10 power minus 22 seconds. For the compound nuclear formation, 10 power minus 17 seconds. So that is the time scale that we are talking about. So when you say compound elastic scattering, it has happened in the time scale of 10 power minus 17 seconds. So the compound nucleus lifetime is a order of minus 17 seconds, and in that lifetime, it is all the projectile and target combined together form a mononucleus equilibrium in all degrees of freedom, and then the subsequent de-excitation of the compound nucleus can take place by emission of particles, gamma rays, and so on. So that is what is called the final stage. So on the way, the projectile can have different types of reactions with the target nucleus, namely elastic scattering, compound elastic scattering, direct reactions, and the compound nucleus formation. These are the main types of reactions and the time scale is, as you go from left to right, time scale of the reaction is increasing. You can also explain the different mechanisms that take place when a projectile bombards a target. And in fact, this is in the context of a projectile which is rather heavy compared to a neutron, a proton, and so on. So when we say this what I have drawn in the schematic is the target nucleus, and the projectile is coming at different distance from the center of the target. So if you recall the previous lecture, we defined the angular momentum involved in a nuclear reaction. And so the angular momentum for the central collisions, that means the impact parameter is 0. So angular momentum, if you recall, equal to V into P, impact parameter into the momentum. So when the impact parameter is close to 0 here, so this is what is the impact parameter. So the central collisions means impact parameter is close to 0. For them, the angular momentum is 0. So it is here. So what I have plotted also here, the angular momentum dependent cross section versus the angular momentum. And so it is nothing but the 2L plus 1, sigma L 12 plus 1, and you can have the transmission coefficient also. So this triangle is actually like 2L plus 1 afterwards also. So for the central collisions where the angular momentum is low, the projectile will be fusing with the target or forming a compound nucleus formation. This is also called as the complete fusion. The projectile and target nuclei fuse together to form what is called as the compound nucleus. When you go to a little bit away, so it is either we go this way or this way, it is symmetric. So this is a impact parameter where they are just grazing. When we say grazing collisions means they just touch and go. So during the touching process, there could be a transfer of few nucleons from projectile to target or target to projectile. So that is why this the grazing collisions lead to transfer reactions. So where they just come and touch each other, and during that time scale, there will be some transfer from one to other. So they are at the higher, so this is what in the higher impact parameter means transfer reactions taking place. And then there are distant collisions which are beyond the physical boundary of the target. So the distant collisions are like Coulomb scattering. They come in the Coulomb potential, in the vicinity of each other's Coulomb potential and escape. So that is like, Rutherford scattering and so on. So as we go away from the target center, the angular momentum is increasing, and so the different reactions are taking place that I have tried to explain. And so the different cross sections for different processes, compound nucleus, transfer reaction, the Coulomb scattering will not come in the category of nuclear reactions because they do not come in the vicinity of the nuclear potential of each other. The nuclear reactions take place when they come, they experience the nuclear potential of each other. And so if they only come in the Coulomb potential of each other, so we say they are not nuclear reactions. So cross section, sigma L versus L will take care of only the nuclear reactions like compound nucleus, direct transfer, and so on. Okay, let us now see these reactions in more details. The first type of reaction, though we will not call it as a, the reaction cross section does not include the elastic scattering also, but it's good to know exactly what are the different types of processes that are happening in the elastic scattering. So in the elastic scattering, as I have mentioned already here, this is a projectile and this is the target. The projectile and target collide with each other and they go away from each other, retain their identity. So they remain as A, small a, and capital A. Secondly, the most important is that the kinetic energy is conserved. The kinetic energy is conserved means the projectile and target may have some energy EA, like for example, it could be 0. So it can transfer some kinetic energy to the target nucleus. Suppose this is 0. Normally, when the target nucleus is stationary, then EA is 0. Now, the projectile can transfer some part of its energy to the target nucleus. Both of the projectile and target are now having some kinetic energy. That's what is happening, no? When your projectile is colliding with target, then they can go in different direction. So some energy of projectile has been given to the target nucleus, but it remains as kinetic energy. So total kinetic energy of projectile and target after the scattering is same as that of the projectile. That's what we mean that the kinetic energy is conserved. So it is only it can be transferred from projectile to target during the collision, but it is not lost, or it is not transformed to other type of energy like excitation energy and so on. The important criteria in elastic scattering is that the kinetic energy is conserved. So I have given an example of neutrons. When the neutrons are reducing their energy, they are moderated. So they collide with the target material like A, and in the process, neutron will give some kinetic energy to the target nucleus. So the final energy of neutron and target nucleus is equal to initial energy of neutron. And if you recall the previous lectures, then the energy of the target nucleus, maximum energy that can be given to target nucleus can be given 4 Mn Ma, the energy of neutron into Mn plus Ma square. And so, for example, when A equal to 1, then Ea equal to En. That means if the mass of the neutron and mass of the target nucleus is same, like hydrogen, proton, then it can give all energy in one collision. So proton, that is why we say hydrogen is the best moderator. In one collision, all energy of neutron can be given to hydrogen. So hydrogenous material will reduce the energy of neutron fastest. So that is the reason why we say hydrogen is the best moderator. Moderator means we are trying to reduce the energy of neutron from whatever energy neutron has to begin with, and we are trying to thermalize. So the number of collisions that is required to bring the neutron to thermal energy is called the how many collisions are taken. So that number is much less for hydrogen. If you have a higher mass number material, you will require more collisions. For hydrogen, even one collision is sufficient. So that is the way we explain the moderating power of a target material for neutrons. Next type of reaction is the elastic scattering. In elastic scattering, again it says it is in the name itself reveals it is scattering. That means the projectile and target retain their identity, like A plus A dash plus A star. So I have put a star because now the kinetic energy of projectile is not conserved. Some part of the kinetic energy of projectile is transferred to a target nucleus, so the target can get excited. So total kinetic energy before and after the scattering is not conserved now. So some part of kinetic energy was transferred to target nucleus and its excitation energy. And in fact, such reactions, though the masses of the projectile, the reactants and products are same, but the target is now in a, suppose you have the target, it is now excited state, A plus A going to A. So it is excited plus A dash. So this much is the Q value of this reaction. Though it is the nucleus is same, the mass in terms of the masses, the Q value is 0, but this much energy is tied up. So this excited state of nucleus has an excitation energy, and that much energy is required from the initial projectile energy. So you can say the Q value is not constant. The Q value is less than 0. So Q value is also given as EA plus EA dash minus EA. So now this value is negative because some part of the energy of the projectile has been transferred to excitation energy. In fact, there are applications of inelastic scattering in the form of some ion beam reactions. This is called the particle-induced gamma emission, PIGY. So you can have excitation of a target nucleus, and then this excited nucleus can emit a gamma ray, and that gamma ray carry the signature of that nucleus. So if you count the gamma rays, these are prompt gamma rays emitted instantaneously. So then this technique, this is an ion beam analysis technique for material characterization. So when you bombard the target nucleus with a projectile like proton, so PP dash, in inelastic scattering of proton with target materials of aluminum, silicon, phosphorus, and so on, then the excited nuclei of aluminum, silicon, and phosphorus, they de-excite by emission of its characteristic gamma rays, and these gamma rays can be measured by a germanium detector, and so the intensity of the gamma ray essentially tells you the concentration of these elements. So for the material characterization, the inelastic scattering is utilized in as a form of ion beam analysis technique. So this is a simple setup for PIGY. You have a scattering chamber. It can be having a diameter of 50 centimeter or even more than that under vacuum, 10⁻⁶ star or better. And we have a target nucleus, target material in the form of a foil or a pellet. And so the projectile will be going in the forward direction. But this, whenever there is a inelastic scattering, then the gamma ray can be emitted in all directions, and you put a detector at 90 degree, because in the forward detector you cannot keep the detector, because there will be a projectile beam will be passing through the 0 degree. So you put at 90 degree, the background is much less, and you detect the gamma ray. So you can put a HPG at 90 degree with respect to the projectile beam and record the gamma spectrum. It's an online experiment. While the beam is falling, gamma rays are being measured. You measure it for some time, and then so you record the gamma spectrum of the products that are formed. So these characteristic gamma rays tell you what are the elements. If you take the peak area and you can use some standards, you can find out the concentration of these elements in the material. So impurities or even bulk material characterization can be done using inelastic scattering. Then comes the direct reaction. The direct reaction happens in a very short time scale of the order of 10⁻22 seconds. Essentially, this time scale is because of the time that nucleus projectile will take to cross the nuclear dimensions. So that happens in the region of 10⁻22 seconds. And so the direct reactions means they come in the nuclear potential contact, which is there, but they don't amalgamate to form a compound nucleus. So the energy is not equilibrated, the mass is not equilibrated. They just, one-step process. You just knock out an electron, a nucleon, a proton or a neutron from the nucleus, or it can strip its new particles in a very short time scale. So the type of reactions that are taking place are like this DP reaction, deuteron colliding with the target nucleus and a proton is coming out. So deuteron is stripped of a neutron. That neutron is captured by the target nucleus. Like here, 27 aluminum DP, 28 aluminum. Similarly, alpha tritium, alpha is stripped of one neutron and tritium is going out. Neutron is fusing with the target. Alpha D, a deuteron is fused with target, and the one deuteron goes out. So like that, this mostly you will find these reactions take place with the low Z nuclei like lithium, helium, tritium, deuteron, and so on. One of the very interesting aspects of this direct reaction, particularly here the transfer reaction, is you are transferring a neutron from deuteron to aluminum-27, which the energetics are quite different from if you consider a neutron captured by aluminum-27. When a neutron is captured by aluminum-27, then the energy that is released is binding energy of neutron in aluminum-28, 7.7 MeV. So this is the mass of neutron plus mass of 27 aluminum minus mass of 28 aluminum. This is the energy released, and this much energy will go in the excitation of aluminum-28. So the de-excitation of aluminum-28 from 7.7 MeV will take place by the emission of gamma rays. Whereas by DP reaction, you are not exciting this to that high energy because the Q value is different for this reaction. And so if you consider the nucleus in a different excited state, neutron plus 27 aluminum, 28 aluminum, then you will find the in the case of neutron capture reaction, you may populate it here. But in the case of DP reaction, you may populate it here. And so you see a different energy state populated in this kind of stripping reaction. So you can study the nuclear reactions at different energy state and different angular momentum. Another type of reaction is pickup reactions. That means a projectile picks up a nucleon, like here a neutron, here a proton to neutron, and so on. So projectile picks up a particle, a nucleon or a cluster from the target, like here, nitrogen 14 PD. So proton is becoming neutron and escaping. So it is picking up a neutron from nitrogen 14 and goes out as a neutron. So this kind of reactions are also direct reactions. And they all take place at a much smaller time scale. So I try to give a schematic of this. Neutron comes close to the target nucleus and then picks up a neutron from the target nucleus. And so this is a stripping reaction, not the pickup reaction. The neutron comes to the target nucleus, gives a neutron to the target nucleus, and proton is going out, and the target plus neutron nucleus is going in the direction. So these are the kind of reactions, where you populate the low-lying states of the nuclei, because their Q values are not very high. And in fact, the nuclear physics people who study such reactions, they study the spectroscopy of low-lying states by using transfer reactions of stripping or pickup type. So here, it is the momentum transfer. So when you say nuclear reactions, the projectile and projectile wave, you can rate e raised to psi equal to e raised to I kx, like plane wave. So k is the momentum of the particle, and so when for example here this DP reaction, so the projectile is transferring a neutron to the target nucleus. So the neutron momentum can be given in terms of proton momentum, the neutron momentum, and like a vector sum of proton and neutron momenta to give you the neutron moment. So how much momentum is transferred to the target nucleus, that is Kn, and that can be given in terms of, so you know the momentum of the proton, you know the momentum of the neutron, so you can tell how much is the momentum transferred to the target nucleus, and that momentum then you can transform to the angular momentum in terms of r cross p. So p is kh cross, and r maximum, since they are peripheral collisions, they are surface reactions, so r can be replaced by the nuclear radius. So the angular momentum transferred in these nuclear reactions are the neutron momentum and the radius of the target nucleus. So they are the kind of reactions where you transfer some angular momentum, and you can see those target states having that kind of angular momentum. So people are trying to see spectroscopy of low-lying states of target nuclei by means of this direct reaction. So the nuclear physics community trying to study spectroscopy of low-lying states utilize these beams of lower charged particles like protons, neutrons, so on, to study the spectroscopy. Okay, so now I will come to the last nuclear reaction mechanism, and that is the most important one, that is the compound nucleus reactions. In the compound nuclear reaction, the projectile and target fuse together to form a compound nucleus C, and subsequently this will be excited by emission of particles or gamma ray. So we can say this is an ejectile and this is the heavy residue. We will discuss more on this subsequently. The important aspects of this are the projectile and target lose their identity. That means the compound nucleus does not know what way it was formed. Kinetic energy is not conserved in the compound nuclear reactions. All the energy, most of the kinetic energy of the projectile will be converted into the excitation energy of the compound nucleus. The projectile and target nucleus fuse to form a compound nucleus. So formation of compound nucleus is the first step. It's a two-step process. In the first step, projectile target fuse together to form a compound nucleus, and second step, the compound nucleus de-excites by emission of particles and gamma rays. And the most important part is these two steps are independent of each other. So whatever is the projectile exercise energy and angular momentum, they decide how it will decide. It does not depend upon how the with projectile and with target fuse together to form this components. So this is the important assumptions, and they have been verified also subsequently. So the compound nucleus is called intense channel, means A plus A is called the intense channel, how it was formed. So for the intense channel, that means formation of compound nucleus from projectile and target, we will call as the first part of the reaction, and that is called the intense channel. Intense channel means how the projectile entered the target to form the compound nucleus, and for that the Q value is mass of the projectile plus target minus the mass of the compound nucleus into, you can say, C square. To write in terms of the delta M values in MeV, then we don't need to multiply by the C square. Secondly, the energy available in the center of mass system, ECM, is equal to projectile energy in the laboratory into mass of target upon mass of target plus projectile. So it is the mass fraction of the target to total mass. Suppose the target is heavier, then the majority of the energy of projectile goes to center of mass energy, and a small fraction will go into the kinetic energy. So what goes as the kinetic energy? EA into MA upon MA plus MA. This fraction is also called as the required energy. So some part goes as required energy, some part goes as the ECM, energy available in the center of mass system, and that energy available in the center of mass system adds to the excess energy of the compound. So the compound nucleus excess energy is equal to energy available in center of mass system, ECM, plus the Q value. And the another important property of compound nucleus is the angular momentum of the compound nucleus, which is the projectile angular momentum plus target angular momentum, and the orbital angular momentum that the projectile brings in, the L value for a particular collision. So these are the spins, and this is the orbital angular momentum. They couple vectorially to give rise to a resultant angular momentum. So the net de-excitation of the compound nucleus depends upon excitation energy and the angular momentum. These are the two important properties of the compound nucleus that will govern how the nucleus will decay. The independent hypothesis I was talking about, that means the formation of the compound nucleus and its decay. These are two independent steps in the compound nuclear mechanism, and this has been verified by one experiment of an Indian scientist S.N. Ghoshal way back in 1950. And very interesting experiment he carried out. That is, he formed a same compound nucleus, zinc 64, by two different reactions. Alpha plus nickel 60, zinc 64, proton plus copper 63, zinc 64. And this compound nucleus is excited. This excited compound nucleus can emit a neutron, two neutrons, or proton and neutron, giving rise to different products, zinc 63, zinc 62, and copper 60. So what I have shown here on the left hand side in this graph is the variation of the cross section of a particular product formed by two reactions. For example, this first reaction, let us see zinc 63, one end product. Zinc 63, here you can see nickel 60, alpha N, zinc 63, copper 63, Pn, zinc 63. So for nickel 63, for nickel 60, this is the reaction, and for copper 63, this is the reaction. So you can see here both the ratio of the two, the cross section for the two channels, different interchannels, are nearly constant. This small difference in the cross section value actually may be due to angular momentum, because it is very difficult to match excitation energy and angular momentum. So you can see the proton energy and alpha energy are matched, so that will give you the same excitation energy, but angular momentum could be slightly vary, and that's why there could be small difference. But by and large, you see other product, copper 62, alpha Pn and ppn, Both the reactions give to similar cross section. Zinc 62, you can see the whether you form by nickel plus alpha or copper plus proton, the cross sections for the individual products are nearly same. That was the experimental verification of the independent hypothesis. That means whatever channel you use to form a compound nucleus, the excitation of the compound nucleus is independent of that. That is what I tried to explain using the experiment of S.N. Ghoshal for a compound nucleus process. I will stop here and take up the detailed mechanism of compound nucleus in the next part. Thank you.